In lesson IA3, we're going to make a change, whereas the first two lessons were, I hope, review topics in algebra. I think that we may be starting something that may be a little unfamiliar to some of you, and so I want to take it at a pace that will be good for everyone. The first thing that we are going to talk about the concept of radicals. And a radical is a root. So when you see this symbol, that is a radical sign. I'm sure you've seen it before. Before we go into it much, I think it might be a good idea to make a chart that said if x is 1, then if you square it, 1 times 1 is 1. If you cube it, 1 times 1 times 1 times 1 is 1. And if you raise it to the 4th power, it's 1. 2. When x is 2, x squared is 4. X to the 3rd power, meaning 2 times 2 times 2 is 8. And 2 to the 4th power is 16. 3 squared is 9. 3 cubed is 27. 3 to the 4th power is 81, and so on. Your calculator can be very helpful, and don't forget that you have a symbol if you want to raise 3 to the 4th power, that on the calculator it is 3 exponential key, which looks like the housetop, and then 4. Depending on your calculator model, it might end up looking like this. It might end up looking like this. But either way, these would be equal to 81. So I will show that as we need to in the lesson. All right, just as an introduction to square roots, oops. All right, the square root of 4 is equal to 2 because 2 squared is 4. The square root of 25 is 5 because 5 squared is 25. Let me go ahead and mention that there are other roots. We won't concentrate on them a lot, but we will see them. Suppose I said, what's the cube root of 27? The cube root of 27 is 3. Look at your chart. In the cubes, find 27. Its cube root is 3. This is called an index, and it tells you what kind of root you're working on. When there is no index, it's implied to be a 2. So the cube root of 27 is 3 because 3, that's the base, to the 3rd power is 27. When you take a square root, it is sometimes called simplifying the root. So if I write the instruction simplify, and I say, would you simplify the square root of 49? Well, I'm saying, what would you have to square to get 49? And the answer is 7. Let's look at your calculator for just a minute. Wait for that to load. It seems to be a little slow. All right, here's our calculator. I'm going to clear the screen. And the square root symbol is down the first column on the left, and it is a second function of the x squared. So if I want to take the square root of something, I have to press second, then the square root key. I get a radical. Let's say I'm taking the square root of 49. If for some reason I need to get out of the radical, I would push the right arrow key. But if that's all you're doing, you don't have to worry about getting out of it. Press enter. And the square root of 49 is 7. If I want to take other roots other than square roots where the index is different, then I look at the math menu. That's the third key down on the first column. And you can see that choice number 4 is cube root. So if I choose a number 4, depending on the model of your calculator, it may look like that. It may not look as good as that. But let's suppose that I take the cube root of 64. You remember in our list, if you looked under cubes for 64, you would see that its cube root is 4. So press enter, and we get 4. If you hit the math key again, and you want to take some higher root, you would choose number 5. But we'll talk about that in a few minutes, assuming that we need it. Okay? So, to simplify means to take the square root. If I had the square root of x squared, that would be equal to x, because x to the second power is x squared. If I said what's the square root of x to the 6th, it would be x to the 3rd, because x to the 3rd squared, we would use our power rule for exponents, that's one of the reasons we studied them, is x to the 6th. The square root of x to the 10th is x to the 5th. So I hope you're beginning to see a pattern when you have variables with exponents, that when you take their square roots, you're taking half of the exponent. Let me erase this. Now, if we talked about cube roots, say I said, would you simplify the cube root of 125? You could use your calculator to do this. All right, I should have left that screen up there, because cube root, I go math. I choose number 4. You can either scroll down and hit enter, or you can just type a 4. That says choose item number 4, 125, enter. And to simplify that, we get 5. You won't have a lot of the next kind, but there will be some. If I ask you to take the cube root of x to the 3rd, you would get x, because x raised to the 3rd power is x to the 3rd. That seems a little silly. If I said what's the cube root of x to the 12th, it would be x to the 4th, because x to the 4th raised to the 3rd power, power rule, is x to the 12th. So once again, I hope you see the pattern that if you have if you have variables with powers, when you want to simplify cube roots, you're dividing 3 into that exponent. With square roots, you're dividing that invisible 2 into the exponent. Now, a little bit more to do with simplifying. Let me get us some more space. What if we have a non-perfect square that we want to simplify? So please keep in mind that my instructions are to simplify. If I have perfect squares, then I take their square roots. If I have perfect cubes, I take the cube root. But what if I had the square root of 20 and somebody asked me to simplify it? Now, you can, of course, just put that in your calculator and get a decimal value, but that is not simplifying it. That is getting a decimal approximation for it. I can't find a number that if I square it, I get back to 20. This is what it means to simplify a square root that's a non-perfect square. It means to factor it. Now there's several ways to factor 20. Certainly I don't want to use 1 times 20, but I could use either 2 times 10 or 4 times 5. And so it's very helpful to think about your multiplication facts. You choose the factorization that has as one of its factors a perfect square. Put the perfect square in the first radical, put the non-perfect square, sometimes I call the leftover, in the second radical, and now simplify what you can. You can simplify the square root of 4. It is the rational number 2. you can't simplify the square root of 5, and so this is considered a simplified form of the square root of 20. The simplifying of non-perfect squares can be challenging sometimes because you really have to think about your factoring. What if you were asked to simplify the square root of x to the 7th? Well, remember up here, we said we divided that invisible 2 into 6 and got x to the 3rd. Or divided that invisible 2 into 10 and got 5. Well, this invisible 2 does not go into 7 evenly. So I do something similar that I did over here. I have to factor it, but it is so easy to factor variables with powers. Thinking about undoing the product rule, it could be x times x to the 6th. It could be x to the 2nd times x to the 5th. It could be x to the 3rd times x to the 4th. And I think that'll be my choices because the product rule says the sum of the exponents has to equal 7. Well, to simplify, you want the largest perfect square, and for a variable with an exponent to be a perfect square, it must have an even exponent. The largest one is x to the 6th. There is a leftover x to the, and we wouldn't write it, but it is an invisible 1. So if you just take 1 away from an odd number, you get an even number. You can simplify that to be x to the 3rd, radical's gone, times the square root of x. This is a description of the process of simplifying radicals, and now we're going to spend time doing that. All right, let's look at problem number 1. It says to simplify by factoring, and they ask us to simplify the square root of 18. Well, you will have to think about factors of 18. In this case, I could say, well, is it 3 times 6? Is it 2 times 9? I choose 2 times 9 because when I factor this, I need a perfect square, and I need the largest perfect square. Well, the only perfect square is 9, and then 2. Something you can do, going way back up here, is look in your squared column and see what is the largest number in that column that divides into the 18. And by the way, the number inside the radical is called the radicand. The little number out here is called the index. The number inside is called the radicand. The largest perfect square that divides into 18 is 9. So this becomes rational 3, because you take the square root of 9 to get rational 3, times the square root of 2, and that is considered simplified. Let's look at number 2. It says to simplify 3 times the square root of 27. Now this 3 is just kind of a tag-along factor. You can sort of ignore it. I'm going to break the square root of 27 into 2 factors, and one of them has to be a perfect square. The largest perfect square that will go into 27 is 9, and it is 9 times 3. You could have used your list, you could have worked with the factors. So I keep this rational 3 in front. I take the square root of 9, which happens to give me another factor of rational 3, and I keep the square root of 3. My final answer will be 9 times the square root of 3. That is considered the simplified version of this. All right, let's look at number 3. It says to simplify the square root of 90. All right, so the square root of 90. Sometimes you can do this in pieces if you don't get the largest perfect square first. The first thing that came to my mind was that 9 is a factor, and it is 9 times 10. So let's go ahead and say this is 3 times the square root of 10. You should always pause there and ask yourself if the square root of 10 has any perfect square factors, and it does not because it only has 1 and 10 and 2 and 5. So this is considered simplified. What's going to happen is you're going to work with several numbers in this lesson, and you're going to simplify them, and you're going to kind of remember some of the factorizations. All right, let's look at number 4. This time they've invited a variable with an exponent. All right, what I'm going to do for the square, I'm sorry, that was kind of an ugly radical. Sometimes my radicals are not the prettiest. 100x to the 9th. I'm still going to factor it into 2 radicals with the front radical always containing the perfect square factors. Well, the numerical coefficient is 100. That is a perfect square, so the whole thing goes there. X to the 9th. Because that exponent is odd, it is not a perfect square factor. X to the 9th is not. I will drop it by 1, making it x to the 8th and putting a single x over here. Because remember, the product rule says x to the 8th times x to the implied first gives you x to the 9th. So I have it factored. Take the square root of the front factor. The square root of 100 is 10. The square root of x to the 8th is x to the 4th, because remember, you're dividing the invisible 2 into the 8, and it's times the square root of x, and that is the simplified version. Now we're going to do a little bit with cube roots, and maybe even some other roots, but we'll see. All right, we are asked to simplify the cube root of 16x to the 4th. I would recommend that you look in your chart for a perfect square. I'm sorry, rephrase. Look in your chart for a perfect cube. Look in the x cube column and find a number that goes into 16. And you will find, don't forget your cube symbols, you will find that 8 is a perfect cube and it goes into 16. It's 8 times 2. Now x to the 4th. Remember that this exponent needs to be divisible by the index. Well, if I take 1 away from 4, I'll have 3, and I can put the single x back there. Now, my front radical, 8 is a perfect cube, x to the 3rd is a perfect cube. The cube root of that is 2x times the cube root of 2x. When you do it in my math lab, you just have to use a tool that allows you to pick a radical and put in the index. There is help in my math lab if you're not sure how to enter those. All right, here's one that is a 4th root, but these are powers, so they will actually be easier. The 4th root of f to the 8th, g to the 7th. All right, I do exactly the same thing I have been doing. I factor it into 2 radicals. They are both 4th roots. F to the 8th, because 4 divides into 8 evenly, I can put f to the 8th in the perfect radical. But 4 does not go into 7 evenly. Now, on all my previous examples, I've been able to just take 1 away from that power and it was divisible. But if I take 1 away from that, in other words, if I write g to the 6th in the first one and g in the second one, that's not divisible by 4. So that's not a good way to factor it. If I take 2 away from it, I would have g to the 5th and g to the 2nd, and that's still not divisible by 5. Sorry, that's not divisible by 4. But if I take 3 away from it, and I have g to the, if I take 3 away, it leaves me with g to the 4th, and I put the 3 there, 4 and 3 still add up to be 7. So I looked at all the choices that add up to be 7, but my goal is to leave something divisible by the index in the front one. So I will keep 4 factors of g up here and send 3 factors of g back here. I know that it's a good factorization because 4 plus 3 equals 7. That was the product rule with exponents. When I take this 4th root, remember that I divide. That's going to leave me with f to the 2nd, g to the invisible 1 that you will not write, times the 4th root of g to the 3rd. We'll do some of those, but we're not going to focus on that very much. All right, let's look at number 7, going back to square roots. If I'm supposed to simplify the square root of y to the 13th, I need to factor it because it's not a perfect square, and I need to get an exponent that is divisible by the 2. Well, if I just take 1 away from that, remember that's 1, that will leave me 12 of them up there, and that is divisible by 2. I end up with y to the 6th times the square root of y. That's what it means to simplify a radical. Let's look at number 8. Put several things together. What's the square root of 81, a to the 6th, b to the 7th? Okay, I have numerical coefficients and I have variables with powers. Nevertheless, I still am going to factor. The front radical will contain all perfect square factors. 81 is a perfect square, so I don't have to worry about it. A to the 6th is a perfect square because its exponent is even. B to the 7th is not. But if I take 1b away, that will leave me with b to the 6th, kind of an ugly 6. Now, this radical contains a perfect square. This has the leftovers. I have 9, a to the 3rd, b to the 3rd, times the square root of b. And that is the simplified form. All right. Next one. This radical is negative on the outside, and that simply means that I'm going to drag that along with me in the problem, and my answer will have a negative on the outside also. All right, I have to work on 180, and 180 is not a perfect square. If you make an entire chart, or a pretty good chart, you'll see that it does not fall under the perfect square. So I just start, honestly, I'm going to say I'm going to play with it for a minute. All right, so I'm just going to, what I'm calling play with it. I'm going to factor this, and you've probably done factor trees before. This is a method I like to use when I have a larger number and I can't just see what the largest perfect square is that goes into that. But somebody might see 9, that it is 9 times 20. Now, this is a perfect square, so I drew a square around it, but I don't know that it's the largest perfect square. This is what I'm going to do. Look at the other factor. Does it still have a perfect square as a factor? And the answer is yes, 4 times 5. By doing this in stages, I was able to kind of whittle it down a little, and here's something you may not realize. Most people haven't realized it. If you multiply a perfect square times a perfect square, the answer you get will be a perfect square. What this tells me, and I know this is kind of just, it would be like written in the margin, negative square root square root. 36 is the largest perfect square that goes into 180. So I'll put 36 here. Now, what's the other factor? Well, if you need to, you get your calculator and say, well, what's 180 divided by 36? And the answer is 5. Okay. Now, the variables are so much easier. If they're even, they're perfect squares. So x to the 8th is a perfect square. Y to the 19th is not. I will take one of those y's back here, leaving 18 of them here. So now it's even. Now that factor is a perfect square factor. I'm going to keep my negative. The square root of 36 is 6. X to the 4th, because I divided by 2. Y to the 9th, divided by 2. And I cannot do anything with the square root of 5y. We are hopefully getting more confident and better at simplifying radicals. Let's look at just a couple of others, and then we may move on to doing some other operations with radicals. We've been doing mostly factoring these. If I'm asked to simplify the square root of 63, I want you to think for a minute. What's a perfect square factor of 63? So in your head, all your multiplication facts probably are scrambling around, and hopefully you came up with 9 times 7. The square root of 9 is 3 times the square root of 7, and that's it. This one asks you to simplify the square root of x to the 11th. Okay, 11's not an even number, so when I do my factoring, I know that I'll take 1 back over here, and that leaves me with 10 of them up here. It's easiest to do this when you're dealing with square roots. The square root of x to the 10th is x to the 5th, divided the 10 by 2, times the square root of x, done. We have a couple of problems where they ask us to simplify, and it looks like the square root of a fraction, but let me make something very easy for you. To take the square root of a fraction, all you have to do is break that radical into the square root of the numerator over the square root of the denominator. We will have more lessons where we work with things like this. Our problems in this lesson are rigged, so these are perfect squares. The square root of 1 is 1. The square root of 49 is 7. And the answer is 1/7. The rational fraction, 1/7. Using that same technique, I will break this into the square root of 25 over the square root of 16. So that's 5 over 4. And that's all I have to do. The next few problems, they're going to ask me to multiply and sometimes divide radicals, and it may seem like you're kind of running around in a circle, because I'm going to say the following. Simplify anything you can at the first, then multiply, and then simplify again if you have created a perfect square under the new radical. So for this first one, the first thing I'm going to do is see if I can simplify either one of these. The square root of 2x, there's no perfect square factors in there, so I will leave it. But, well, maybe I'll just write it over here. The square root of 2x cannot be simplified, so I leave it. But the square root of 121x can be simplified, because 121 is a perfect square, x is not. That means it is rational 11 times the square root of x. So I simplified this factor, if I could, but I couldn't. I simplified this one because I recognized pretty quickly that 121 is a perfect square. So then I write down the first factor, and I write down the second factor, and I multiply, and you multiply radicals by multiplying their rational coefficients. Well, there's an invisible 1 times an 11 is 11. And I am sorry, that was an x. I hope you were waiting for me to get that fixed. So the 11's on the outside. Multiply the radicands. That's 2x squared. So I simplified, then I multiplied, and now I'm going to see if I can simplify again, because many times you create a perfect square through the multiplication. I'm going to keep the 11, and I can simplify this. Now I can't do anything with the 2, so he goes back here with the non-perfect squares. But x squared is a perfect square because the exponent is even. That means that I get 11x, so this is where the 11 is. The square root of x squared is x. The square root of 2 is simply the square root of 2. My answer is 11x square root of 2. Now, it seems like you kind of went in a little circle. I recommend that at the beginning of the problem, you simplify what you can. Then you multiply. How do you multiply? You multiply the outer numbers if there are any, and you multiply the radicands if there are any, and then you simplify again if you can. All right, let's look at it, and we'll be doing something very, very similar on this one. All right, it asks us to multiply, but remember what I said. Take each one of them. I have the square root of 4x squared. Can I simplify that? Yes. As a matter of fact, that entire radicand is a perfect square, so that's 2x, radical gone. This factor, it's the square root of 12x. Well, 12's not a perfect square, x is not a perfect square, but I can break 12 into 2 factors, one of them being a perfect square. So it is 4, perfect square, times 3. The x is not a perfect square, so it goes back here in the non-perfect square radical. Take the square root of 4 is 2, square root of 3. All right, that means that I have 2x times 2 square root of 3. Some people disagree with my method. They would say just multiply them and simplify what you get. But unfortunately, sometimes you get very large quantities and it becomes difficult. So now I will multiply these. Remember, this is, I'm not going to call it scratch work, but it is preliminary work. And I multiply rationals, which are things on the outside, and then radicals, if there are any. So 2 times 2 gives me 4 times x times the square root of 3. I ask myself one more time. I simplified. I multiplied. Can I simplify again? This time the answer is no. I'm done. Number 16. Now this time it says do the quotient rule. Well, we can do exactly the same thing. You can simplify and then divide. The difference between the quotients and the products, if you were to multiply first, you build bigger radicands. But when it is division, if you divide first, you create smaller radicands. So I recommend that you go ahead and divide first. So I'm going to divide, these are both radicands, 3 into 27, that's going to give me 9. And remember the quotient rule? Let me write this like this. This is the same as 27x to the third over 3x, all under 1 square root. And so you can divide. 3 goes into 27 9 times. Use your quotient rule with exponents, which tells you to subtract. And now simplify your answer. That is 3x. So when it's a quotient, I say go ahead and jump right in and divide if you can, because simplifying will be easier. Number 17, this is the square root of 60x to the 8th over 5x. I'm going to go ahead and divide. 5 goes in there, it's under the radical, 12 times. When I do division with exponents, I use the quotient rule, which tells me to subtract. 8 minus invisible 1 gives me 7. Now I need to see if I can simplify this, and I believe I can. Perfect square radical, non-perfect square radical, factor the 12, perfect 4 times 3, factor the x to the 7th, leave 6 of them up front, send 1 to the back. Take the square root of this, it'll give you 2x to the third square root of 3x. And I believe number 18 is our last problem. So we're going to have to do exactly what we've been doing. Put it under one radical. It is 32x to the 7th over 4x to the negative 7th. Well, I'm going to go ahead and divide. 4 goes into 32 8 times. Now, how do I do this? The quotient rule says that it will be x to the numerator 7 minus denominator power of negative 7. That means that I have the square root of 8x to the 14th. Why? Because minus means plus. Now can I simplify that? Yes. 8 can be factored into 4 times 2. X to the 14th is a perfect square because 14 is a perfect square. It's an even number, I'm sorry. So that gives me 2x to the 7th times the square root of 2. So the main objective here, after just talking about what radicals are, is to simplify radicals. It's a very important skill, and you will see it throughout this entire semester.